Okay, in this video, we're going to look at how delta G, how the value of delta G will change with temperatures. We looked at that in a little bit in the last one when we looked at the thermal decomposition of calcium carbonate. We saw delta G was positive at low temperatures, and as the temperature increased, it became less positive, eventually became zero, and at that point, the reaction was possible. Okay, so if you look at our equation for delta G is equal to delta H minus T delta S. And if you remember back to your GCSE maths, you will know that the equation for a straight line, remember it was y is equal to mx plus c, where m was the gradient and c was the intercept on the y-axis. Okay, so what we're going to do here is we are going to plot, we're going to get a graph, and we're going to plot delta G on the y-axis, and we're going to plot the absolute temperature on the x-axis. And you notice I'm not going into the negative bit because you can't have negative absolute temperatures. So delta G is going to be y. What's changing in this? What's x? Well, x, the thing that's changing is the absolute temperature. So we're going to plot absolute temperature on the x-axis. That's going to be x. So you can see that means that our intercept is going to be equal to delta H for the reaction. So the intercept on the y-axis is going to be there. And m, that's really important, m is going to be equal to not delta S, but minus delta S. The gradient is equal to negative of the entropy change. So if let's say we had, I'll just draw, okay, that line like that. Let's say if we had a reaction which followed that blue line, well, what would that tell us? We'll look at our intercept there. The intercept, that is delta H, and that is positive. So this would be an endothermic reaction. That means it's endothermic. And the well, what's the gradient? The gradient is negative. So therefore, that means that delta S for that reaction would be positive. So this is an endothermic reaction where delta S is positive, and you can see, right, and this would be very like the reaction we just looked at in the calcium carbonate one, wasn't it? Yeah, calcium carbonate went to calcium oxide and CO2. So that was an endothermic reaction, but the entropy change was positive because we're making this carbon dioxide gas. So we can see here in this part of the graph, reaction is impossible. So at low temperatures, no, it's not going to happen. But when you get to this value of T, that's the minimum temperature at which the reaction can occur. And any temperatures in excess of this, of course, you're in this negative bit of the line there that's below the x-axis. Delta G is negative, so the reaction can occur. Right, so we're going to use this to, there are only 4 kinds of reactions really then, aren't there? Well, because you can either have delta H can be positive, or delta H can be negative, and delta S can be positive, or delta S can be negative. So we've got 4 combinations there, which I've done below here. So we have a look at one I did earlier. Right, so there we've got them all. Right, let's have a look at, well, this is the one we were just looking at here, wasn't it? An endothermic reaction, delta H positive, okay, and delta S, so positive, so we've got an increase in entropy, an increase in entropy in the reaction, but it's endothermic. that line, delta H, well, our intercept is going to be up there, isn't it? The gradient is going to be negative because delta S is positive, so you're going to get a line like that. That's the one we just looked at. And a good example of that reaction here is, right, is the thermal decomposition, blue, thermal decomposition of calcium carbonate. That's a really good example of that sort of reaction. Solid going to calcium oxide, solid, and CO2 gas. Another example of that we had in an early video was cracking. Okay, so we had, like, you know, C10H22 liquid. Get a big increase in entropy here because you get a lot of gas. You get 4 moles of ethene gas and 1 mole of ethane gas, but it is an endothermic reaction. Okay, so those sort of reactions are only possible after you get past that temperature there. Low temperature won't happen. So reaction, let's write down there, reaction possible at high temperatures. Okay, so let's have a look at the this one here now in the bottom left. So the only thing we changed there is we have got delta H is negative this time. So delta S, we changed 2 things there. Sorry, delta H is negative and delta S is negative as well. So where is our line going to go? Well, delta H gives us the intercept, so that's going to be down here, isn't it? It's negative. Delta S is negative, so that means the gradient's going to be positive, so it's going to go that way, like that. So this kind of reaction then, this reaction is only possible at low temperatures. Once you get past that temperature, delta G becomes positive, doesn't it? So it can't happen. So let's write down reaction possible only at low temperatures. So let's see a good example of that. Right, magnesium ribbon burning. That is a very good example of that sort of reaction. So, and we've come across that in an early video. So we've got magnesium solid plus a half O2 goes to MgO solid. Right, how do we know it's exothermic? Well, we know it's exothermic because, you know, you burn a piece of magnesium ribbon, it's very, very exothermic, it's a bright white light, very hot and all that. Why is the why is delta S negative? Why is that? Well, the entropy goes down because you started off with oxygen, which is a gas, and you're forming magnesium oxide there, which is a very highly ordered ionic solid. So entropy goes down, and that's what's going to happen there. So if you try and burn a piece of magnesium ribbon when the temperature is too high, it won't work. It won't burn. I think the temperature is really high, about 4,000 degrees C or something. So, you know, but nevertheless, that is true. Right, let's have a look at the top. No, let's look at this one first of all. Okay, bottom right. So here, delta H is negative, and the entropy increases. Okay, right. A good example of that is burning carbon. Okay, so in blue, sorry. So if you get carbon, solid, and you combine it with oxygen, you'll get carbon dioxide gas. Now you know that's exothermic because obviously if you have a barbecue or something, you burn charcoal on a barbecue, you get loads of heat out, very exothermic. How do we know that delta S is positive? Sorry. Okay, well, that's not quite so obvious to know that delta S is positive there. It's not quite so obvious, but you've got carbon, which has got a very low entropy, and you've got oxygen, which is a gas, forming carbon dioxide, which is also a gas. And if you look at the if you look at the numbers in the data book, you'll see that delta S is actually positive for that reaction. Right, what's the graph going to look like then? It is going to be, so we've got intercept down here, yeah, delta S is negative, delta H is negative, sorry, the intercept is there, and the gradient, well, the gradient's going to be negative because delta S is positive, so that's going to go like that. Your line is going to go like that. So you can see that the delta G is always negative. It's always negative. Look, never goes above the axis yet. So that means this reaction is feasible at all temperatures. It's possible at all temperatures. Possible at all temperatures. Right, now the last quadrant, which we haven't done yet, is right delta H positive and delta S negative and delta S positive as well. So before I think of a reaction there, I'm going to put in, so that goes there, doesn't it? Delta, the intercept is positive because delta H is positive. The gradient is going to be, sorry, that should be a negative there, shouldn't it? Sorry. The gradient is going to be positive because delta S is negative, okay? And so that means that line is going to go like that. So you can see that reaction, delta G is always positive, never goes below the axis, so that means that that reaction is impossible at all temperatures, okay? So in other words, there aren't any reactions like that. So I can't give you a reaction for that one. There aren't any. But if you wanted to cheat a little bit, you could say, right, we can consider, right, let's have carbon dioxide carbon dioxide decomposing to form carbon and oxygen. Well, we know the backward reaction is exothermic, so the forward reaction in this direction must be endothermic. We know the backward reaction, you get an increase in entropy, so the forward reaction there must be a decrease. So that would be like a sort of theoretical possibility of yet. Of course, that can't happen, so I'll put a big red cross there. That reaction never happens. So it's a good idea to have those four graphs in your head, all the four examples, so you really understand which reactions, how delta G varies with temperature, and how reactions can, become feasible or unfeasible as the temperature changes. That's really a useful thing to have. Just one little word of warning there. These graphs are idealized. Okay, so I've drawn my graph, delta G and T, and I've got it's going like that. In actual fact, you get kinks where the gradient changes in these lines sometimes, and that's because you get delta S can change. Sorry, S changes very suddenly for a reactant, for example, due to changes of phase. In other words, saying if something turns into a liquid from a gas, it's obviously going to get a big jump in the value of S, so you're going to get a change in the value of delta S at that point, so you'd get a kink. So in reality, you're not going to get a straight line for every possible temperature. You're going to get some changes, but don't worry about that. It's still a pretty good way of determining which reactions can occur at which temperatures. Very often they ask calculations. Here they might ask you, we've done this one, they'll ask you the minimum temperature at which this reaction can occur. And what you do there, you make delta G is equal to 0, and then you just rearrange it and work out the value of T. And this one here, they might say, what's the maximum temperature this can occur? Another exam question. And again, you make delta G is equal to 0 and just rearrange and work out the value of T. So that is more or less finished the whole Gibbs free energy and entropy topic. And if you remember that equation, delta G is equal to delta H minus T delta S, then you can't really go far wrong.